5.2 is now getting into different ways of computing probability. It's called the addition rule and complements. So there's a key difference between 5.2 and 5.3 that I'm going to try my darnest to make sure you understand. All right? So the first definition we have going here, guys, two events are disjoint if they have no outcomes in common. Okay? So meaning if I do one and I do the other and they don't have anything that they share in the sample space, they would be considered disjoint. Another name for disjoint is mutually exclusive. Mutually exclusive. All right. So the book, we'll use those interchangeably. I might as well, too. But like if I have a question and the answer is disjoint, you can either answer it disjoint or mutually exclusive. Like you can use either or, whatever you feel comfortable with. How they show this is using Venn diagrams. So I don't know if you guys ever have taken a set or a logic class where they use Venn diagrams. So Venn diagrams, the entire rectangle is the sample space. So all these numbers are in the sample space, and then each circle represents an event. So this is a Venn diagram where we have numbers 0 through 9 in the sample space, but event E is only numbers 0, 1, and 2, and event F is just 8 and 9. So these are outside of the events. These are in events E, these are in event F. But do you agree that E and F share nothing in common? So they're called disjoint. And what do you think of disjoint means not together, right? Like not connected. So if you look at those are not overlapped at all. So if they are disjoint, the rule is you can just, if you want to know the probability of E or F happening, you can just take the probability of one plus the probability of the other. They don't share anything in common, so just this or that can happen. So let's add them together. The second part, guys, is just showing you we can expand it to however many little events we need to as long as they're disjoint. So notice the sample space is still the same, 0 through 9. But now we have E, F, and G. But again, they don't overlap. They're all disjoint. So these are all disjoint. So guess what the rule is? The probability of one plus the probability of the other plus the probability of the third. You could have event H in there and so forth. So let's go ahead and look at the top of page 5. At the top of page 5, we have a fair die is rolled. We want to compute the probability of rolling a 6 or an odd number. So this is what I do. Instead of calling it E or F, I just write it as it'll make sense. So the probability of 6 or an odd. The probability of being a 6 or an odd. Can you roll one die and can it land on 6 and an odd number at the same time? No, because if it lands on 6, it's not odd, right? So these are two mutually exclusive events. You're either 6 or you might be an odd number, but you can't be both, all right? So these are mutually exclusive or disjoint, so it's just going to be the probability of getting a 6 plus the probability of getting an odd number. I'm just showing this just to show you the rule. The probability of E or F equals the probability of E plus the probability of F. All right, so let's jump into the actual probabilities. This is a perfect example of classical probability. We don't actually have to roll our die. When we roll our die, how many numbers can we get? 6. So what's our denominator for each? 6, right? Because when we roll our die, there's 1 through 6 that can happen. Let's just focus on the first event. The probability of rolling a 6. Of those 6 numbers, how many is the number 6? Just 1. So do you guys agree that we have a 1/6 chance of rolling the number 6? That's just the number 6. All right. And you can even write that. Like you might write like my little sample space, you know, my little event. Oh, not 6, 1. I want 6 there, not 1. The number 6 is the one number I can roll. It's 1 out of 6, right? How many on that die are odd, though? 3. What numbers? 1, 3, and 5, right? So again, look at them separately. What's the odds of getting a 6? One of those numbers is 6, so 1 out of 6. What's the odds of just getting an odd number? 3. So how many total numbers would I be happy with? 4 out of 6. Do you think my math lab will take that? Nope. They're going to say reduced fraction or percent or decimal, okay? So let's write this as 2/3 or 0.67 or 67%. You know what? One of those is what it's going to ask for. But I like to come back because I feel like the pre-simplified version makes the most sense. How many total numbers are there? 6. But of those 6 numbers, how many we'd be happy with? We'd be happy with the number 6 or any of the odd numbers, 1, 3, and 5. That's 4 numbers of the 6 we'd be happy with. So that sum shows you right then and there that we have 4 numbers we'd be happy with, which reduces to 2/3. All right, let's go to the next one. We have a standard deck of cards, and we're just drawing a card. Compute the probability of selecting a 10 or a jack. Can you pick one card that's both a 10 and a jack? No. So those are mutually exclusive. So the probability of a 10 or a jack will just be the probability of a 10 plus the probability of a jack. All right, this is where you might get out those little like goldenrod color sample cards I gave you. How many total cards are in a deck of cards? 52. So that will be the denominator for each of them. And of those 52 cards, how many 10s are there?
4.
4. You got it. And how many jacks are there? 4, right? So when it comes down to it, when I draw a card, I'd be happy with 8 of them. I'd be happy with any of the 10s or any of the jacks. So I have an 8 out of 52 chance of getting the card I want. Is my math lab going to be happy with that? No. What's a really easy way to reduce this? It's my favorite. It's, you know you're a math teacher when, ... I need to make my own book. You have a favorite button on the calculator. It's my favorite button on the calculator. It's the Math Frac button. Does everybody know where that is? So if you can do that part, 8 out of 52 in your head, but you're like, God, I don't want to stop here and think about reducing it. I'll turn the light on real quick. All right, you just type your fraction 8 out of 52, which we want to reduce. If you hit math, the very first thing highlighted is fraction. Enter, enter. It reduces any fraction for you in simplest form. So that will be 2/13 there. My favorite button, okay? So 2/13, or what's 2 divided by 13? We'll do like, I'll put or 0.15 or 15%, or, you know, whatever they want you to round to there. Did everybody see where that was? Math Frac? Are there any questions with the addition rule? All right. They're typically pretty nice with you, and they usually give you things that have common denominators. If not, you can just do the math on here and hit Math Frac, and it'll find the common denominator for you and everything. Life would be all sunshines and rainbows and kitty cats and gumdrops if everything was mutually exclusive, but it's not, okay? When we start rolling die and drawing cards, we can have common events, okay? So there's a little bit of overlap. So here's just the Venn diagram that's showing it. So if we want to know the probability of getting something in event E, we have 5 of them. The probability of event F, we have 4 of them, but who did we count twice? The numbers 1 and 3, okay? So when you have this overlap, you need to count them once, but you don't need to count them twice, okay? So the general addition rule, guys, is the rule to remember. Why am I stressing that? Because it still works for mutually exclusive events, all right? So don't think that you have to memorize one and then the other. Just memorize this one, okay? And I'll show you what I'm talking about. So the probability of E or F, if the 2 events are not mutually exclusive, would be the probability of the first plus the probability of the second minus the and, what they share. So notice it says and, not or, okay? It's what they share. So in this one, we'd have the probability of E, which is 5 out of 10, plus the probability of F, which is 4 out of 10, minus the probability of E and F, which is 2 out of 10, because they share 2 things. And we would get the probability of getting something in E or F, all right? So let's look at these 2 examples. It says a fair die is rolled. What's our denominator in the 6, without even having to do it, right? Compute the probability of rolling a number less than 3 or an odd number. So the probability of a number less than 3 or an odd number. And I'm not going to even stop and think, is this mutually exclusive or not? I'm just going to do the general addition rule because it'll get me no matter what. Oops, let me write it like that first, okay? So the probability of getting a number less than 3 plus the probability of getting an odd minus the probability that they might share something that's less than 3 and odd. So the probability of getting a number less than 3, so the first event by itself, plus the probability of getting an odd number, the second event all by itself. At the very end, you worry about what they share. Okay, so we actually can start with the probability of a number less than 3. How many total numbers are we rolling or could happen? 6. Of those 6 numbers, how many are less than 3? 2 of them. The number 1 and the number 2. So 2 out of 6 are less than 3. And again, if you want to do your little sample space down here, those are the numbers that are less than 3. There's 2 of them. So that's where my numerator came from. All right, you move on to the odd. We just did that right up top, right? How many total numbers are there? 6, but how many were odd? 3. The numbers 1, 3, and 5. Okay? By writing our little baby sample spaces like that, what do you notice? What happened when we added the probability of a number less than 3 plus the probability of odd? What happened when we added those two together? We shared 1, right? So we're double counting 1. We shouldn't count twice, okay? So what do we have to do? We have to minus the probability of getting a number less than 3. That's odd. So how many total numbers are there out there? 6. But how many are less than 3 and odd? 1. Because it's the number 1, okay? These don't match. This matches how many things are in that set. For example, I can have the exact same thing, but a number less than 3 and even, right? What numbers are less than 3 and even? The number 2, but what number would still be up here? 1, because there's only one number that's less than 3 and even. So you do your, I feel like we get the same number every time. So you do your math. 2 plus 3 is 5. 5 minus 1 is 4, 6. But again, before we reduce, I like to talk about this. This just shows you what numbers you'd be happy with. What numbers are less than 3, 1 and 2, and what numbers are odd, 1, 3, and 5. But we already counted 1, so we just want to add 3 and 5 to it. There's 4 numbers we'd be happy with. But MyMathLab only will be happy with the reduced or the decimal or the percent. It will tell you what it wants. Why can this work even for these up here? I'm going up here, guys. Going back to the top. You could put it in right here, minus the probability being 6 and odd. What's the probability of getting a card that's 6 and, or a number that's 6 and odd? 0. So minus 0. Have I changed anything? No, but I didn't forget to subtract when I needed to subtract. So I actually do them all with the general addition rule. What's the probability of getting a 10 and a jack? 0. So you can put 0 out of 52 on the back there. All right, let's look at this one down here. A card is drawn from a standard deck. So one card's being drawn. We want to compute the probability of getting a queen or a red card. All right? So the probability of a queen or red. Well, according to the general addition rule, we're going to do the probability of the first event, a queen, plus the probability of the second event, a red, minus the probability of getting a card that's a queen and a red. Because they do overlap, so we don't want to overcount anything. So see how I'm doing the probability of event E, the first guy, plus the probability of event F, the second guy, minus the probability of E and F. So all of these denominators are going to be 52 because we're drawing cards. So I just flew through there, keeping my signs the same, but I know my denominator is going to be 52. So this again is kind of checking on you guys and knowing how well we know our deck of cards. Of those 52 cards, how many are queens?
4.
4 of them. You got it. So we have a 4 out of 52 chance of getting a queen. This is kind of a weird way, but I like to keep our denominator the same, and you don't have to necessarily. But But of those 52 cards, how many are red? 26, right? Half the deck. So if you wanted to do 1 out of 2, you could. Or you can say I have 13 diamonds and 13 hearts. So I have 26 cards that are red. All right, think about it now. Of those cards, how many are queen and red? I heard it.
8. No. Queen and.
You're actually getting to the answer. So I'll come back to you, Caitlin, because you actually got the answer without having to do this formula at all. But 2 of them are going to be a queen and red because we have the queen of hearts and the queen of diamonds, okay? So these are just all 4 queens, right? These are 4 queens. These are all the red cards. But this is the queen of hearts and the queen of diamonds, right? So here we counted all 4 queens. The queen of hearts, the queen of diamonds, the queen of spades, the queen of clubs. But here we did all the red cards, 2 through ace in red, you know. But who did we count twice? Well, we counted these 2 queens when we counted the queens, but we counted them here as well because they were red. So how many total cards are we actually happy about choosing?
28.
And that's what I was going to say. You're getting right to it because we know half the deck's red. So we would be happy with half the deck. There's 26 cards. What other cards would we be happy with? The other 2 queens, exactly. And so that's another way to think of it as well. 20 out of 52, we don't know what it reduces to, so guess what you can do? You can do it in your calculator. 28, oopsie, turn your calculator on. 28 out of 52, hit math frac, 7 out of 13. If you want to change it to a decimal, you can. That's 0.54 for rounding, or 54%. And that makes sense because we would be happy with more than half the deck, right? Because half the deck was the red, and the couple other queens that we'd be happy with puts us over the edge of 50%. All right, so that's how we can use that general addition rule for classical method, because it's just stuff that we know. We didn't have to actually, I should bring a deck of cards and we should start playing the odds to see if we should go to Vegas. I'll try to ask Dr. Chapman if they'll sponsor a trip to Vegas. Can we have a field trip? All right, so sometimes you can use this method for empirical data as well, so data that's in a chart. So here's a chart that's made up of 100 people, 50 are male, 50 are female, but then we also asked, are you left-handed or right-handed? So there was 80 that are right-handed and 20 that are left-handed, all right? So we want to compute the probability of getting a left-handed person or a male. So the probability of left hand or male. So here's my E, there's my F, okay? So according to the general addition rule, it's the probability of the first, a left-hander, plus the probability of the second, just a male, not specific, just any male, minus the probability of getting a left-hander and a male. Okay? So it's the probability of the first plus the probability of the second minus the probability that you could get one that is both. All right? So we're choosing from everyone. So what's our denominator for everything? Keep that in mind because it's very easy to like focus on just the males because you see the word male, or just the left-handers because you see the word left-handed. But we're just choosing any one from this group. And there's a total of 100. So 100 is going to be our denominator for each of them. All right. So again, don't think of left-handed males yet. Just think of left-handers. How many of those 100 people are left-handed? Oops. Nope. Yes, you're right. Sorry, I was looking at the wrong one. 20. So 20, I'm like, you're right. And you're like, what? How do I say it any different? Out of the 100 people, a total of 20 are left-handed. All right? Now ignore left-handed and just focus on the male. Of 100 people, how many are just male? 50, okay? Again, don't keep left-handed in your mind. It's just simply male. The 12 will come in here in a second, okay? So what's the probability of strictly being left-handed? 20. What's the probability of strictly being a male? 50. But how many are left-handed and male? 12. And it's kind of where we cross, right? When we do the left-handers, we do this row. When we do the males, we do this column. And who got counted twice? The left-handed males. Okay? So we got to subtract that out. And again, I would just do the math. 20 plus 50 is 70. Minus 12 is 58 out of 100. But that reduces to 29 out of 50. Does that look right? Or as a percent and decimal, 58 or 58. So it doesn't matter whether they give you a chart of data or it's just the classical method. Keep in mind your denominator is always everyone you're picking from. So not just the males of 50 or not just the left-handers of 20. Those are your numerators, okay? We're picking from 100 people each time, strictly left-handed, strictly male, and then what do they share? All right, so the last idea is this complement rule. And it's complement with an E, not an I, so it's not like, oh, I like your hair. It's the math complement, all right? So what it is, it just basically means the opposite. Okay? So it says, let S denote the sample space of a probability experiment, and let E denote an event. The complement of event E, first of all, it's denoted with an E and a little c, is all the outcomes that are in your sample space, but that are not in E. So basically, the opposite of E. Depending on your book, this will change. Like some books use E prime, some books use E bar. These are all just different symbols of complements, all right? This specific author uses a little c, okay? So let's come up with the complement here. So it says, let E be rolling a prime number. What would be in our sample space if E was rolling a prime number? Well, we talked about this, I think, on Wednesday. A prime number was 2, 3, and 5. Remember how we talked about that? No, sorry. Yeah, that's right. I'm thinking odd. So a prime number is any number that just has two factors, 1 in itself, right? So 2 just has 1 and 2, 3 just 1 and 3. So what would be the complement of E? It'd be every other number we could get when we roll the die other than 2, 3, and 5. What would that leave? 1, 4, and 6. You got it. So everything other than E. Right? It's everything other than E. So when you roll a die, in your sample space you have 1 through 6. E are the numbers 2, 3, and 5. So that leaves the complement to be everything else. Well, we didn't list 1, 4, or 6, so that's the complement of E. You're like, okay, big whoop, who cares? Well, it's important because a lot of times we might not know the probability of E, but we know the probability of E complement. And it's easy to go hand in hand, okay? So what do we know about a sample space? It must total 1, or 100%. And if they are built into each other like this, if one's 40%, one's 50% or 60%, they're going to equal up to that 1 or 100%. So it just says if E represents any event, the complement is always 1 minus, okay? Or you could have the probability of E equals 1 minus the probability of its complement. You can go either way, okay? The probability of the complement is 1 minus E, or the probability of E is 1 minus the complement. You can go either way, all right? So let's look at this problem here. It says, if the probability that you'll pass the class is 85%, what is the probability that you won't pass the class? Well, you guys can do this real quick, but I want to do it using the notation, okay? The probability that you don't pass, we don't know it, right? But don't you agree you're either going to pass or not pass? So they're complements of each other. So the probability that you don't pass is just 1 minus the probability that you pass. So that's just 1 minus 0.85, or what? 15%. If I told you there was a 30% chance of rain today, you could tell me the percent chance that it didn't rain. What's that? 70, okay? So again, sometimes we don't know the probability of a certain event, but we know the probability of its complement, so we can just swap it. We know that they have to equal 1 together, so you just do 1 minus that.